have a signal on the luminosity monitors. We have events.
Knowing the catastrophic dangers this machine could create, many believe this is a technology humans should have never built. With the potential to form black holes right here on Earth, the destruction brought about by its creation could dwarf that of the atomic bomb. This has led to people like Elon Musk publicly protesting, saying these organizations are playing with demonic technologies. What are they truly trying to discover under the ground at CERN? And what happens if they actually achieve it?
Inside the world's largest collider. The Large Hadron Collider, or LHC, is the world's most powerful and largest machine for smashing particles together. It began operating on September 10, 2008, as the newest addition to CERN's complex of accelerators. The LHC is a massive 27-kilometer loop beneath the France-Switzerland border near Geneva, filled with superconducting magnets and other devices designed to increase the energy of particles as they move through. The tunnel is so enormous that the workers use bicycles to get around inside it. Inside this colossal machine, two beams of particles are accelerated to nearly the speed of light, traveling in opposite directions. These beams are contained within separate vacuum tubes and are guided along their paths by a strong magnetic field created by superconducting electromagnets. These magnets, made from special coils of electric cable, allow electricity to flow without any resistance, ensuring no energy is lost. However, to work properly, the magnets must be kept at an incredibly cold temperature of -271.3 degrees Celsius, which is even colder than outer space. To achieve this, the LHC uses a network of liquid helium to keep the magnets chilled and the system running effectively. Thousands of magnets of various types and sizes are used to steer the beams around the accelerator. This includes 1,232 dipole magnets, each 15 meters long, which bend the beams, and 392 quadrupole magnets between 5 and 7 meters in length, which help focus the beams. Just before the beams collide, another set of magnets compresses the particles, increasing the likelihood of collisions. The particles are so tiny that making them collide is like trying to shoot two needles 10 kilometers apart and having them meet precisely in the middle. The entire operation of the accelerator, including its systems and infrastructure, is managed by the CERN Control Center. From this single location, the beams within the LHC are controlled to collide at 4 points around the accelerator ring, where 4 particle detectors, ATLAS, CMS, ALICE, and LHCb, are positioned. The evolution of particle physics. For a long time, we understood the basic elements of nature, like helium, hydrogen, oxygen, gold, and lead, as made up of various types of atoms. A significant breakthrough came when scientists discovered that all atoms are composed of just 3 fundamental particles: protons, neutrons, and electrons. By adding more protons and electrons, we can create different elements and types of atoms. This means that, theoretically, we could build a simple universe using only these 3 particles. However, in the early 20th century, things became much more complicated. Scientists began finding many new particles from cosmic rays, and there was no system in place to categorize them. They used names like pi, sigma, and delta, but the naming system quickly became overwhelming, and they ran out of symbols. To make sense of this chaos, scientists started organizing these particles based on their properties, such as spin, electric charge, mass, and how long they last before decaying. To simplify the picture, they predicted the existence of new fundamental particles called quarks. These quarks, combined in different ways, could explain all the observed particles, leading to the creation of the Standard Model. Initially, only 3 quarks were known, but as research progressed, a 4th, 5th, and 6th quarks were discovered, which supported the model. Alongside quarks, there are leptons, fundamental particles that include the electron and its heavier relatives, the muon and tau, as well as their neutrino partners. The Standard Model also describes the fundamental forces of nature. The weak force, which governs processes like radioactive decay and energy production in the sun, is carried by W and Z bosons. The electromagnetic force, responsible for light and magnetic interactions, is carried by photons. The strong force, which holds quarks together in protons and neutrons, is carried by gluons, which effectively glue the quarks together. While the Standard Model had been incredibly successful in predicting microscopic phenomena, it wasn't complete. The missing piece was the Higgs boson, often seen as the ultimate goal in particle physics. The Higgs boson is like a special key to understanding how other tiny particles get their weight. It's connected to something called the Higgs field, which acts like a magical force field that gives weight to particles like electrons and quarks. This weight, or mass, is what makes particles resist changes in their speed or position when they're pushed or pulled by a force. However, not all tiny particles have this weight. For example, photons, which are the particles that carry light and electromagnetic force, don't have any weight at all. Scientists had predicted the existence of the Higgs boson for over 40 years and used it in their calculations, but it remained undetected. The discovery of the Higgs boson. To create a Higgs boson, particles need to collide with extremely high energy. However, for a long time, physicists were like explorers in the dark, searching without knowing exactly how much energy was required to make this happen. They knew they needed a specific energy level but had no idea what that range was, making their quest all the more challenging and mysterious. The Large Electron-Positron Collider, LEP, located at CERN in Europe, operated from 1989 to 2000. This accelerator collided electrons and positrons, and its collision energy increased progressively from 91.2 giga-electron volts to 208 giga-electron volts. LEP scientists aim to create Higgs bosons by raising the beam energy to conditions conducive for their production. Despite their efforts, LEP was unable to detect the Higgs boson, but it did manage to exclude the possibility of a Higgs boson with a mass below 114.4 giga-electron volt. This exclusion was a significant step in narrowing down the particle's possible mass range. Following LEP, the Tevatron at Fermilab took on the challenge from 1986 to 2011. This accelerator collided protons and antiprotons with collision energies ranging from 1,800 giga-electron volts to 1,960 giga-electron volts. The Tevatron could produce Higgs bosons, particularly for masses under 160 giga-electron volt, which would decay into bottom quark pairs. For higher masses, the Higgs bosons would decay into pairs of W bosons. However, the common occurrence of bottom quark pairs from other processes made it difficult to detect potential Higgs signals. Researchers focused on collisions where Higgs bosons were produced alongside W or Z bosons to improve detection. Despite these efforts, the Tevatron could not definitively detect the Higgs boson due to limitations in data and energy. The Large Hadron Collider, also at CERN, continues to play a crucial role in particle physics after it began operations. The LHC collides protons with collision energies increasing from 7,000 giga-electron volts in 2010 to 13,600 giga-electron volts as of 2022. The higher energy and advanced detectors at the LHC allowed for the creation and study of Higgs bosons more effectively. The LHC's superior capabilities enabled scientists to observe rare decay modes, such as Higgs bosons decaying into pairs of Z bosons, or photons. These rare decays provided clear signals for detecting the Higgs boson, which was challenging with earlier accelerators. On July 4, 2012, the LHC experiments ATLAS and CMS announced the discovery of a new particle consistent with the Higgs boson, marking a significant milestone in particle physics. This discovery confirmed the particle's existence, but further data was needed to verify that it was indeed the Higgs boson. Scientists conducted additional cross-checks, including verifying decay patterns predicted by Higgs theory. The extensive data collection and analysis confirmed that the discovered particle matched the predicted characteristics of the Higgs boson. The discovery of the Higgs boson was the result of decades of research and technological advancements. Each era of accelerators, LEP, Tevatron, and LHC, contributed critical insights and advancements that culminated in this groundbreaking discovery. A new era in particle physics. On October 8, 2013, François Englert and Peter Higgs were honored with the Nobel Prize in Physics for their groundbreaking theoretical work on understanding how particles acquire mass. Their theories predicted the existence of a crucial particle that was later confirmed by the ATLAS and CMS experiments at CERN's Large Hadron Collider. Right after the Higgs boson was discovered, physicists eagerly began investigating its properties to determine whether it was the Higgs boson predicted by the Standard Model or something entirely different. The first step was to measure its mass, which had been the last missing piece in the Standard Model puzzle. They found it to be around 125 giga-electron volts, which is about 130 times heavier than a proton. This mass meant the Higgs boson could decay into various particles in different ways. The discovery of the Higgs boson marked the beginning of an exciting new chapter in particle physics. Scientists focused on understanding this unique particle, which stands out in the Standard Model for its lack of spin, electric charge, and strong force interactions. To confirm these features, they measured the spin and parity by analyzing how the Higgs boson decayed into other particles. The results matched the predictions, solidifying its identity as the Higgs boson. However, it's still unclear whether this is the only Higgs boson or just one among many, as some theories, like supersymmetry, suggest the existence of additional Higgs particles. While some of these theories have been disproven, others still need more data for exploration. By closely examining how the Higgs boson is produced and how it decays, physicists at ATLAS confirmed that it interacts with both bosons and fermions, the particles that make up all matter. This finding further validated the Standard Model's prediction that elementary particles gain their mass through the Higgs field, which permeates the entire universe. The groundbreaking discovery of the Higgs boson was achieved by closely examining how it decayed into various particles, including photons and the W and Z bosons. These decay patterns were crucial because they confirmed the occurrence of a process known as spontaneous electroweak symmetry breaking, a fundamental concept in the BEH mechanism, which explains how particles gain mass in our universe. However, understanding the Higgs boson required more than just these observations. In the Standard Model, the Higgs boson interacts with two different kinds of particles, fermions and bosons, through specific couplings. Any unknown physics could potentially influence these interactions in ways we haven't yet discovered. The first clear evidence of the Higgs boson interacting with fermions came when scientists observed its decay into tau particles, based on combined results from the ATLAS and CMS experiments at the end of Run 1. As Run 2 progressed, with higher energy levels of 13 tera-electron volts and a larger dataset, researchers explored additional interactions. They detected the Higgs boson decaying into bottom quarks and being produced together with top quarks. More recently, the first measurements were made of the Higgs boson's interactions with second-generation fermions, such as charm quarks and muons. These findings have solidified our understanding of how the Higgs boson interacts with the matter particles that make up our universe. Key to particle mass. The discovery of the Higgs boson marked a pivotal moment in our understanding of particle physics, completing the framework of the Standard Model after extensive research. This confirmation validated a fundamental theory about how particles gain mass. Contrary to what might be assumed, the Higgs boson itself doesn't directly grant mass to other particles. Instead, it represents a manifestation of the Higgs field, an all-pervading field in the universe. This field interacts with particles, giving them their mass. But why couldn't mass be simply assumed from the start? To answer this, we need to revisit earlier work in quantum field theory. Quantum fields are somewhat like the familiar electric or magnetic fields, but they also include states that we recognize as particles. These fields are categorized into matter fields, which include electrons and quarks, and force fields, which include photons and gluons. In the late 1940s, scientists successfully used quantum field theory to explain electromagnetic interactions involving photons and electrons. However, the theory struggled with nuclear interactions. The weak nuclear force, with its short range, implied that its associated particles must have mass, unlike the massless photon. Adding mass to these force-carrying particles directly led to problematic predictions that went to infinity. In the early 1960s, researchers sought alternative methods to introduce mass into the theory. Peter Higgs, François Englert, and Robert Brout provided the solution. They proposed that an invisible field fills all of space and interacts with weak force particles to give them mass. This field is not zero, even in empty space, breaking a fundamental symmetry in quantum field theory. Previous theories had suggested a massless, spinless particle, but experiments had ruled this out. Higgs, Englert, and Brout demonstrated how this particle could be absorbed by the weak force particles, resulting in these particles acquiring mass. The only remaining spinless particle was the Higgs boson. Another team of theorists reached a similar conclusion in the same year. Further studies showed that the Higgs mechanism could give mass to not only weak force particles, but also to electrons, quarks, and other fundamental particles. The greater the interaction with the Higgs field, the more massive the particle becomes. However, it's crucial to note that the mass of composite particles, like protons and atoms, comes primarily from the energy that binds these particles together, not from the Higgs mechanism. Supersymmetry, unifying forces and matter. Supersymmetry, often abbreviated as SUSY, is a principle in theoretical physics that has garnered significant attention for its potential to explain some of the deepest mysteries of the universe. At its core, SUSY posits that the equations governing the fundamental forces of nature and the particles of matter should be treated as identical. This elegant concept suggests that for every known particle, there exists a superpartner with different spin properties, effectively doubling the number of particles in the universe. The Standard Model of particle physics, while immensely successful in describing a wide range of phenomena, is not without its limitations. It explains the interactions between fundamental particles and the forces of electromagnetism, the weak force and the strong force. However, it leaves several critical questions unanswered, such as the nature of dark matter, the apparent weakness of gravity compared to other forces, and the origin of the Higgs boson. SUSY offers a potential framework to address these gaps. In the realm of physics, symmetry plays a pivotal role. Symmetry refers to a property where a system remains unchanged under certain transformations. For instance, a sphere appears the same regardless of how it is rotated. In the context of mathematical equations, symmetry implies that changing certain variables or components doesn't alter the overall outcome. The Standard Model itself is built on symmetries, but it distinguishes between the particles that carry forces, known as bosons, and the particles that make up matter, called fermions. SUSY seeks to unify these two categories by introducing superpartners. For every fermion in the Standard Model, Supersymmetry predicts the existence of a corresponding boson, and for every boson, a corresponding fermion. These superpartners are crucial to the symmetry that SUSY aims to establish. If matter and force particles are treated as interchangeable in the equations, the resulting theory would be more balanced and elegant. One of the primary motivations for considering SUSY is its potential to solve the hierarchy problem in physics. This problem revolves around the question of why gravity is so much weaker than the other fundamental forces. SUSY suggests that the existence of superpartners could naturally stabilize the mass of the Higgs boson, preventing it from being excessively large due to quantum corrections. This, in turn, could explain why gravity appears so weak compared to the other forces. Moreover, SUSY provides a compelling candidate for dark matter, a mysterious substance that makes up about 27% of the universe's mass-energy content, but has never been directly observed. The lightest superpartner, often referred to as the neutralino, is a stable, electrically neutral particle that could account for the dark matter detected through its gravitational effects on galaxies. Despite its theoretical appeal, SUSY has yet to be confirmed experimentally. The Large Hadron Collider, LHC, at CERN, has been at the forefront of the search for superpartners. However, no evidence of these particles has been found so far, leading some physicists to question whether SUSY is the correct path forward. Nonetheless, the principle remains a vibrant area of research, with ongoing efforts to refine the theory and explore its implications. SUSY represents a bold attempt to extend our understanding of the universe beyond the standard model. By proposing a symmetry between matter and forces, it offers solutions to some of the most perplexing problems in physics. Whether this principle accurately describes the universe remains an open question, but its potential to transform our understanding of the cosmos ensures that it will continue to be a focal point of theoretical and experimental research. Demonic technology. Elon Musk, the tech billionaire known for his bold ideas and even bolder statements, recently tweeted an image that quickly stirred up conversation. The image showed the LHC with a black skull and the words, "I am normal," and can be trusted with a demonic technology unlike anything the world has ever seen. For those familiar with Musk's online presence, this might seem like another one of his infamous Twitter jests, a playful meme meant to amuse his audience. However, beneath the surface of this seemingly humorous tweet lies a deeper reflection on how public figures like Musk can influence public perception of scientific endeavors. Musk, with his immense following and cultural impact, has the power to sway public opinion with a single tweet. His online persona is a blend of wit, innovation, and occasional cryptic messaging, making his statements more than just social media banter. They often shape public discourse, especially on topics as complex and mysterious as quantum physics and the LHC. By referring to the collider as demonic technology, Musk tapped into the long-standing fears and misconceptions surrounding one of the most advanced scientific instruments ever built, subtly influencing how his followers, and perhaps the broader public, view the LHC, the world's largest and most powerful particle accelerator. Among the most significant achievements of the LHC is the discovery of the Higgs boson. The significance of the Higgs boson discovery can be likened to a story from the childhood of Albert Einstein. As a young boy, Einstein was given a toy compass while he was sick in bed. The way the compass needle consistently pointed north, regardless of how it was moved, sparked a lifelong fascination with the hidden forces that govern the physical world. This simple observation led Einstein to a profound realization. There must be an underlying order to nature, one that he would spend his life trying to uncover. Just as Einstein's compass pointed to something unseen, yet profoundly real, the discovery of the Higgs boson revealed a fundamental aspect of the universe's architecture, offering a glimpse into the deep, hidden order of the cosmos that Einstein once sought. However, while the discovery of the Higgs boson was celebrated as a monumental achievement, it also stirred up new questions and concerns. Some physicists have speculated that the Higgs field might have implications far beyond what we currently understand. For instance, Robert Hogan, a physicist from King's College London, has suggested that the universe might be on unstable ground due to the behavior of the Higgs field during cosmic inflation, the rapid expansion that occurred right after the Big Bang. If the Higgs field had fluctuated too much, it could have caused the universe to collapse into a different energy state, ending everything as we know it. The fact that our universe still exists suggests that there's much more to learn about the Higgs field. The LHC, with its unparalleled ability to smash particles together at near-light speeds, could be key to uncovering hidden particles and solving the mysteries of the universe. Elon Musk's characterization of the LHC as demonic technology taps into the fears and conspiracies that have surrounded the collider since its inception. For years, some have speculated that the LHC could create black holes or other catastrophic phenomena that could endanger the planet. While these theories have been thoroughly debunked by scientists, they continue to persist in the public imagination, fueled in part by the provocative statements of influential figures like Musk. Musk's tweet, though likely intended as a tongue-in-cheek remark, highlights the power that public figures have in shaping perceptions of science. When someone as prominent as Musk speaks, his words carry weight, and they can either contribute to a deeper understanding of complex issues or reinforce misinformation and unfounded fears. CERN sets the record straight. Is it really true that the LHC is a demonic technology capable of opening portals to new dimensions? This theory, which emerged around the time of the LHC's reopening following a brief closure, has stirred up quite a bit of fear and fascination. CERN, the organization behind the LHC, has been clear in its response to these dramatic claims. According to CERN, the LHC is a sophisticated scientific instrument designed to investigate the fundamental components of the universe. Its primary function is to smash particles together at high speeds to observe the resulting interactions, which can reveal new insights into the nature of matter and forces. Far from being a source of supernatural danger, the LHC has been instrumental in making significant scientific advances, such as the discovery of previously unknown particles and the study of theoretical constructs like mini black holes. The notion of the LHC creating a portal to another dimension or releasing dark forces is purely speculative and not grounded in scientific reality. For example, while the LHC can create tiny quantum black holes, these are exceedingly small and pose no threat to our planet or its inhabitants. They are fundamentally different from the black holes typically depicted in science fiction. A CERN spokesperson has addressed these concerns directly, stating that the organization doesn't tolerate this kind of spoof, and that such theories can give rise to misunderstandings about the scientific nature of our work. The LHC remains a vital tool for pushing the boundaries of our understanding of the universe, and its operations are firmly grounded in rigorous scientific research. The Future Circular Collider. CERN is forging ahead with an ambitious project to construct a massive new particle collider along the Swiss-French border. This future collider, named the Future Circular Collider, FCC, is set to be over 3 times larger than the LHC, the very machine that identified the Higgs boson. To build the FCC, engineers will need to excavate an enormous circular tunnel with a circumference of 91 kilometers and a depth of 200 meters. This tunnel would span an area larger than Chicago and facilitate high-energy particle collisions. The estimated cost of the project is around $17 billion. Construction could potentially begin as early as 2033. The new collider will collide electrons with positrons, their antimatter counterparts, to produce and analyze large quantities of Higgs bosons. Scientists believe that studying these particles in such detail could expose weaknesses in the Standard Model, the current framework describing fundamental particles and forces. The FCC aims to achieve particle collisions at energies up to 100 trillion electron volts, 7 times greater than the 14 trillion electron volts maximum of the LHC. The FCC's construction would occur in 2 stages. Initially, in the 2030s, the collider would focus on electron-positron collisions. Later, in the 2070s, it would shift to proton collisions. At the same time, other nations are exploring their collider projects. Japan is considering the International Linear Collider, while China is working on the Circular Electron-Positron Collider. However, not all scientists are convinced that the FCC is the best path forward. Some advocate for a different approach, using muon colliders, which could allow for even higher energy collisions due to the greater mass of muons compared to electrons. Yet, the feasibility of building such a collider remains uncertain. Additionally, there are debates about whether the enormous expense of these projects is justified, especially since the LHC has yet to reveal new physics beyond the Higgs boson discovery in 2012. As researchers continue their quest to unravel the mysteries of dark matter, dark energy, and the matter-antimatter imbalance in the universe, the future of the FCC will depend on forthcoming decisions and developments. The quest for new physics. The discovery of the Higgs boson has marked a pivotal moment in particle physics, offering profound insights into the fundamental structure of the universe. The Higgs boson, often referred to as the God particle, is crucial for understanding why particles have mass and how they interact with each other. Yet, the exploration of its properties is far from complete. Recent advancements in particle physics focus on deciphering not just the Higgs boson's interactions, but also its role in broader cosmic phenomena. Since the initial discovery of the Higgs boson, physicists have accumulated extensive data sets, enabling a deeper investigation into how often the Higgs boson is produced and the various ways it decays. By examining the decay products of the Higgs boson and the angles between these particles, researchers can test specific theories about its interactions. For instance, one area of interest is whether the Higgs boson interacts with tau particles in a way that exhibits charge parity asymmetry. Such findings could provide clues about why the universe contains far more matter than antimatter, potentially solving one of the biggest mysteries in cosmology. An intriguing aspect of the Higgs boson's interactions is its potential for self-interaction, where Higgs bosons interact with one another. This process, predicted to be exceedingly rare, has not yet been observed due to the limitations in the amount of data collected so far. Detecting such interactions could reveal new phenomena and allow physicists to test the properties of the Higgs field itself for the first time. This goes beyond merely confirming the Higgs boson's properties according to the Standard Model. It opens a window to explore physics beyond the currently understood framework. Physicists are also using the Higgs boson as a probe for new physics. By studying how the Higgs boson decays into various particles, researchers are testing theories that predict the existence of new particles or interactions that the Standard Model does not account for. This includes searching for particles that might be produced alongside the Higgs boson or through its decay. One particularly intriguing application of this research is the quest to understand dark matter. Since dark matter is hypothesized to have mass, the Higgs boson should, in principle, interact with it. Researchers are investigating whether dark matter can be produced in collisions involving Higgs bosons or if it influences Higgs boson decays to invisible or undetected particles. To date, Searches for new physics and dark matter through Higgs-boson interactions have not revealed unexpected results, but the quest continues. The ongoing analysis of the Higgs boson is crucial for refining our understanding of fundamental physics and might eventually lead to discoveries that reshape our comprehension of the universe. What do you think about the assertion that the Large Hadron Collider is a demonic technology?